calculate line currents in a delta transformer with unbalanced loads, we will go through a step-by-step process. Firstly, calculate the phase currents. With 3 kV amps, 4 kV amps, and 5 kV amps on phase windings A, B, and C respectively, and a secondary voltage of 120 volts, the phase currents can be determined by dividing the kilovolt amps by the voltage. The phase current I equals 3 kV amps divided by 120 volts, which equals 25 amps. The phase current I equals 4 kV amps divided by 120 volts, which equals 33.3 amps. The phase current I equals 5 kV amps divided by 120 volts, which equals 41.7 amps. Secondly, convert these phase currents to vectors. This involves expressing each current with its magnitude and phase angle. Assume phase is the reference at 0 degrees. Therefore, I equals 25 amps at an angle of 0 degrees. I equals 33.3 amps at an angle of negative 120 degrees. I equals 41.7 amps at an angle of 120 degrees. Thirdly, calculate the line currents using vector subtraction. In a delta connection, the line currents are the difference between the phase current. The line current IA equals I minus IC. The line current IB equals I minus I. The line current IC equals IC minus IB. Fourthly, perform the vector subtractions. This step requires converting the polar form vectors to rectangular form, performing the subtraction, and then converting back to polar form if desired. IA equals 25 amps at 0 degrees, minus 41.7 amps at 120 degrees. To perform the subtraction, convert each vector to rectangular form. 25 amps at 0 degrees is 25 plus J0. 41.7 amps at 120 degrees is negative 20.85 plus J36. Subtracting these gives 25 minus negative 20.85 minus J36, which simplifies to 4.15 minus J36 amps. For IB, subtract IF from IB. IB equals 33.3 amps at negative 120 degrees, which is negative 16.65 minus J28.9. I equals 25 amps at 0 degrees, which is 25 plus J0. Therefore, IB equals negative 16.65 minus J28.9 minus 25, which simplifies to negative 8.35 minus J28.9 amps. For IC, subtract IB from IC. IC equals 41.7 amps at 120 degrees, which is negative 20.85 plus J36. IB equals 33.3 amps at negative 120 degrees, which is negative 16.65 minus J28.9. Subtracting these gives negative 20.85 plus J36 minus negative 16.65 plus J28.9, which simplifies to 4.2 plus J7.1 amps. Fifthly, convert the line current vectors to magnitudes. This gives the actual current value in amps. The magnitude of IA is the square root of 4.15 squared plus negative 36 squared, which equals approximately 36.5 amps. The magnitude of IB is the square root of negative 8.35 squared plus negative 28.9 squared, which equals approximately 29.8 amps. The magnitude of IC is the square root of 4.2 squared plus 7.1 squared, which equals approximately 8.3 amps. Therefore, the line currents are approximately IA equals 36.5 amps lagging voltage by 85.4 degrees, IB equals 29.8 amps lagging voltage by 165.4 degrees, and IC equals 8.3 amps lagging voltage by 61.9 degrees. The process involves firstly calculating phase currents from given kilovolt amps and voltage values, secondly converting these phase currents into vector form with appropriate phase angles, thirdly calculating line currents using vector subtraction based on the delta transformer configuration, fourthly performing the vector subtraction by converting to rectangular form, performing the subtraction, and optionally converting back to polar form, and fifthly determining the magnitudes of the line current vectors to obtain the actual current values in amps. Now let's delve deeper into the intricacies of calculating line currents in a delta transformer under unbalanced load conditions. This involves not only understanding the basic formulas but also grasping the underlying principles of vector algebra and complex power. Firstly, calculating phase currents is the foundation. You've correctly identified that the phase currents can be found by dividing the apparent power in kilovolt amps by the phase voltage. However, it's crucial to maintain consistent units. Given that the voltage is in volts, it's best to convert the kilovolt amps to volt amps by multiplying by 1000. This ensures that the resulting current is in amps. So, I equals 3000 volt amps divided by 120 volts. IB equals 4000 volt amps divided by 120 volts. And I equals 5000 volt amps divided by 120 volts. This yields the phase currents of 25 amps, 33.3 amps, and 41.7 amps respectively. Secondly, converting phase currents to vectors requires assigning appropriate phase angles. In a balanced three-phase system within a BC sequence, the phase angles are typically 0 degrees for phase A, negative 120 degrees for phase B, and positive 120 degrees for phase C. However, when dealing with unbalanced loads, it's often convenient to choose one phase as the reference and express the other phase angles relative to that. In this case, you've chosen phase as the reference, which is a good approach. Therefore, I equals 25 amps at 0 degrees, IB equals 33.3 amps at negative 120 degrees, and IC equals 41.7 amps at 120 degrees. Thirdly, calculating line currents using vector subtraction is where things get a bit more involved. In a delta-connected transformer, the line current is the vector difference between the two adjacent phase currents. As you've correctly stated, IA equals I minus IC, IB equals I minus IA, and IC equals IC minus IB. This is due to Kirchhoff's current law at each node of the delta connection. The line current entering or leaving a node is the sum of the currents flowing into or out of that node. Fourthly, performing vector subtraction requires a solid understanding of complex number arithmetic. Vectors can be represented in either polar form, which is magnitude and angle, or rectangular form, which is real and imaginary components. To perform addition or subtraction, it's generally easy to convert the vectors to rectangular form. The conversion from polar to rectangular form is done using the following relationship. The real component equals the magnitude times the cosine of the angle. The imaginary component equals the magnitude times the sine of the angle. Once the vectors are in rectangular form, you can simply add or subtract the real and imaginary components separately. For example, to calculate IA, which equals I minus IC, we first convert I and IC to rectangular form. I equals 25 amps at 0 degrees, which is 25 plus J0 in rectangular form. IC equals 41.7 amps at 120 degrees, which is negative 20.85 plus J36 in rectangular form. Subtracting these gives 25 minus negative 20.85 minus J36, which simplifies to 4.15 minus J36 amps. To convert this back to polar form, we calculate the magnitude as the square root of the sum of the squares of the real and imaginary components. The magnitude of IA is the square root of 4.15 squared plus negative 36 squared, which equals approximately 36.5 amps. The angle is calculated as the arctangent of the imaginary component divided by the real component. The angle of IA is the arctangent of negative 36 divided by 4.15, which equals approximately negative 83.4 degrees. Therefore, IA equals 36.5 amps at an angle of negative 83.4 degrees. You can repeat this process for IB and IC to find their magnitudes and angles. Fifthly, converting line current vectors to magnitudes provides the final result. The magnitude of a vector represents its length or amplitude. In the context of electrical currents, the magnitude represents the root mean square value of the current. As you've calculated, the magnitudes of the line currents are approximately 36.5 amps, 29.8 amps, and 8.3 amps respectively. These values represent the actual currents flowing in the lines connecting the delta transformer to the load. In summary, calculating line currents in a delta transformer with unbalanced loads requires a combination of circuit analysis, vector algebra, and complex number arithmetic. By carefully following these steps and paying attention to the details, you can accurately determine the line currents and ensure the safe and efficient operation of the transformer. Furthermore, it is important to consider the implications of unbalanced loads on the transformer itself. Unbalanced loads can lead to unequal heating of the transformer windings, which can reduce its lifespan. It can also cause voltage imbalances in the system, which can affect the performance of other equipment connected to the same power source. Therefore, it is always desirable to balance the loads as much as possible. This can be achieved by carefully distributing the loads among the three phases or by using load balancing techniques. Additionally, it is important to select a transformer that is adequately sized for the expected load. The transformer should be capable of handling the maximum load on any phase without overheating or exceeding its voltage regulation limits. The National Electrical Code, or NEC, provides guidelines for sizing transformers and conductors based on the expected load. It is important to consult the NEC and other relevant standards to ensure that the transformer is properly installed and protected. When working with electrical systems, it is always important to prioritize safety. Transformers can be dangerous if not handled properly. Always energize the transformer before working on it and follow all safety precautions. Use appropriate personal protective equipment such as gloves and safety glasses, and ensure that the work area is well lit and free of hazards. If you are not comfortable working with electrical systems, it is best to consult a qualified electrician. They have the knowledge, skills, and experience to perform the work safely and correctly. They can also help you select the right transformer for your needs and ensure that it is properly installed and protected. Remember that electrical systems are complex and can be dangerous if not handled properly. Always prioritize safety and consult a qualified electrician if you have any questions or concerns. Understanding the principles of transformer operation, vector algebra, and complex number arithmetic is essential for accurately calculating line currents and ensuring the safe and efficient operation of electrical systems. By following these steps and paying attention to the details, you can master the art of calculating line currents in a delta transformer under unbalanced load conditions. Now, let's consider some practical examples of how these calculations are used in real-world applications. Imagine you are designing an electrical system for a small commercial building. The building has a variety of loads, including lighting, air conditioning, and office equipment. These loads are not perfectly balanced among the three phases. You need to select a transformer that is adequately sized for the expected load and that can handle the unbalanced conditions. To do this, you would first estimate the load on each phase. This can be done by adding up the power consumption of all the equipment connected to each phase. You would then use the methods described above to calculate the line currents. Based on the line currents, you can select a transformer with a suitable kilovolt amp rating and voltage regulation. You would also need to select conductors that are sized to carry the line current without overheating. The NEC provides tables that specify the ampacity of different conductor sizes. In addition to sizing the transformer and conductors, you would also need to provide overcurrent protection for the system. This is typically done using circuit breakers or fuses. The overcurrent protection devices should be sized to protect the transformer and conductors from overload in short-circuit conditions. The NEC provides guidelines for selecting overcurrent protection devices. Another example is in an industrial setting such as a manufacturing plant. Manufacturing plants often have large and complex electrical systems with a variety of loads, including motors, welders, and heating equipment. These loads are often highly unbalanced. To ensure the reliable operation of the plant, it is important to carefully analyze the electrical system and to select equipment that is capable of handling the unbalanced condition. This may involve using special transformers that are designed for unbalanced loads or using load balancing techniques to distribute the loads more evenly among the three phases. It may also involve using harmonic filters to reduce the levels of harmonic distortion in the system. Harmonic distortion can be caused by nonlinear loads such as variable frequency drives in electronic equipment. Harmonic distortion can cause overheating of equipment and can interfere with the operation of other equipment connected to the same power source. In addition to the technical aspects of calculating line currents and sizing equipment, it is also important to consider the economic aspects. Transformers and other electrical equipment can be expensive, so it is important to select equipment that is cost-effective. This may involve using energy-efficient equipment or using demand-side management techniques to reduce the overall load on the system. Demand-side management techniques include things like using timers to turn off lights and equipment when they are not needed and using variable speed drives to reduce the energy consumption of motors. In summary, calculating line currents in a delta transformer with unbalanced loads is a complex task that requires a thorough understanding of electrical engineering principles. However, by following the steps outlined above and considering the practical and economic aspects of the system, you can design and operate electrical systems that are safe, reliable, and cost-effective. And it is important to continually learn about new technologies and techniques in the field of electrical engineering in order to stay up to date and to provide the best possible service to your clients. This includes attending conferences, reading technical journals, and taking continuing education courses. By staying informed and up to date, you can ensure that you are providing the best possible solutions for your clients' electrical needs. And it's also important to network with other electrical engineers and professionals in the industry. This can provide valuable opportunities to learn from others and to share your own knowledge and experience. Networking can also lead to new business opportunities and collaborations. So, make sure to attend industry events and to connect with other professionals on social media and other online platforms. And it is good practice to always follow ethical guidelines and professional standards in your work. This includes being honest and transparent with your clients and colleagues and always acting in their best interests. It also includes maintaining confidentiality and protecting sensitive information. By adhering to ethical guidelines and professional standards, you can build trust and credibility and ensure that you are providing the highest quality service possible. Also, it is important to be aware of the environmental impact of your work. Electrical systems can have a significant impact on the environment, so it is important to design and operate them in a sustainable manner. This includes using energy-efficient equipment, reducing waste, and minimizing pollution. It also includes considering the life cycle of the equipment and the impact of its disposal. And always seek to improve your skills and knowledge continuously. The field of electrical engineering is constantly evolving, so it is important to stay up to date on the latest technologies and techniques. This includes taking continuing education courses, attending conferences, and reading technical journals. It also includes seeking out mentorship opportunities and learning from experienced professionals in the field. By continually improving your skills and knowledge, you can ensure that you are providing the best possible service to your clients and that you are contributing to the advancement of the electrical engineering profession. So, in essence, the calculation of line currents is a multifaceted task that is essential for the design, operation, and maintenance of electrical systems. It requires a strong foundation in electrical engineering principles, a thorough understanding of vector algebra and complex number arithmetic, and a commitment to safety, ethics, and environmental sustainability.